Welcome to Yaka Digital Network. If you look at a traditional clock, like the one on the Makerere University Tower, time flows in one continuous, smooth sweep. Every fraction of a second exists. In electronics, we call this continuous physical flow an analog signal. Compare that smooth sweep to sending mobile money on your smartphone. When that transaction processes, there is no continuous middle ground. The money is either in your account or it isn't. It's an absolute, discrete event. The physical analog world has a major flaw. Imagine an analog radio signal traveling across Uganda. As it moves through the air, it inevitably picks up electrical interference. We call this noise, and as you can see in this wave diagram, the random spikes permanently distort the continuous signal. To stop this degradation, engineers realized they had to abandon continuous values entirely. They developed a system that ignores the physical messiness of the real world and relies on a binary language of just two distinct states, 0 and 1. This binary language is driven by microscopic silicon components called transistors, which act as simple switches. They have exactly two states. If a transistor is on, receiving a high voltage of typically 5 volts, it represents a 1. If it's off, at 0 volts, it's a 0. Because these two binary states are completely separate from one another, there is no room for ambiguity. A digital system can easily ignore the physical noise that would ruin an analog signal, isolating only the clear zeros and ones. But raw zeros and ones need specific rules to be useful. To actually make decisions and automate real-world tasks, like securing a busy shop in Kampala, we route these signals through fundamental circuits called logic gates. Take an alarm system. You want the alarm to sound if either the front door opens or a pressure sensor on a window is triggered. This is an OR gate. As this truth table shows, the mathematical output, the alarm, becomes a 1 if at least one input sensor is a 1. Contrast that with a Ugandan maize milling machine, which needs stricter safety rules. You only want the engine to run if the master switch is on and the safety guard is closed. This is an AND gate. The table shows the output is 1 only when both inputs are exactly 1. There is also the NOT gate. It acts as a simple inverter that completely reverses whatever input it receives. Feed it a 1, and it outputs a 0. By stacking these microscopic logical rules together, machines can replicate complex conditions. This allows us to automate heavy industrial machinery and intricate security grids without any human intervention. To build these systems at scale, engineers favor a specific universal building block, the NAND gate. Operating as the exact opposite of an AND gate, NAND gates are incredibly cheap to manufacture, and they can be combined to replicate the function of any other logic gate. When you shrink and pack millions of these NAND gates onto a single silicon wafer, you get an integrated circuit. This density gives chips incredible processing power, but it creates a logistical problem. How does a digital chip, operating strictly on 5-volt logic, communicate with a variable analog environment like a soil moisture sensor on a farm? The hardware solution is shown in this schematic, a potential divider. By placing two resistors in a series circuit, we can step down a high real-world voltage into a specific, safe fraction that the delicate microchip can actually read. Once the voltage is safely scaled down, we need a software translator. The analog to digital converter, or ADC, takes that variable analog voltage and translates it into binary data. It does this through a process called sampling. Because a digital system can't record a continuous flow, the ADC takes incredibly fast, distinct snapshots of the continuous curve. It chops the smooth analog data into a blocky digital approximation made entirely of zeros and ones. Without translators like potential dividers and ADCs, the massive computational power of integrated circuits would be completely blind and deaf to the physical world. So why did the world abandon analog for digital electronics? It comes down to error correction. Look at how an analog wave and a digital pulse wave travel down a wire side by side. As they travel, physical interference corrupts both signals, but the analog wave becomes permanently destroyed. Because the data relies on the exact shape of the smooth curve, the random noise merges with the original data, and it cannot be untangled. Now watch the digital signal pass through this logic gate. Even if the binary pulses get severely distorted by noise, the system only needs to recognize the threshold of a 1 or a 0. The gate reads the messy pulse, identifies it as a 1, and outputs a mathematically perfect, clean signal on the other side. This microscopic architecture of zeros and ones shields information from the chaos of the physical universe, making flawless, high-speed data processing a reality. Every automated marvel you rely on today is built entirely on this simple, error-free foundation of on and off. Thank you for learning with the Yaka Digital Network. To explore more classes, visit us at www.yaka.cc.